Here we are on page 3 of trig functions, equation identities, addendum. First thing we're going to do is we're going to talk about the domains and ranges, or the possible x's and the possible y's for the arcsine, arccosine, and arctangent functions. Those are the inverse functions for each one of those trig functions. And, even though the sine function, cosine function, and tangent functions, basically their domains are all real numbers, except for the tangent function, which has the exception of the asymptotes. It's all real numbers except for the asymptotes. Obviously, when you take the inverse function, when you basically reflect these functions about the y equals x diagonal line, like we did on the previous problem here, you're going to have a situation where the reflected functions are not functions because they don't pass the vertical line test anymore, right? So what we need to do is we need to cut off certain parts of the original trig function before we reflect it, so that it'll still pass the vertical line test. Okay? So basically, if you take a look at this function here, this is the sine function, right? So how would we make it so that the sine function basically represents every possible y value, but not more than once? And the way we do that is we are going to take this part of the sine function. We're going to take this part of the sine function right here, and we're going to consider this to be the domain from here to here and the range from here to here that we're going to use when we define the inverse sine function or the arcsine function. The reason why they probably chose this part of the function is they really want to have the x equals 0 point as part of the domain. And notice that if you choose the x equals 0 point here, that you pretty much have to go a little bit to the right and a little bit to the left in order to take on all possible values of y from -1 to 1, right? Because if you tried to include this part of the sine function, then you would start repeating values here, right? And we do want the x equals 0 value, right? So we're limited to this part here. And what's this point here? This point here is 90 degrees or pi over 2, right? So this x value here would be negative pi over 2. So our restricted domain in this case is going to be negative pi over 2 to pi over 2. Okay, so we can write it like that. Now for the restricted range, we know that we're going to take on all values between -1 and 1, so we can write -1 to 1, and that is the y value that ranges between -1 and 1. What about cosine? Let's take a look at the cosine function here. It starts at 1, goes down to -1, and it goes up to 1. Now, as usual, we want to include the x equals 0 point, which is right here. Then we want to include all the points on the cosine function so that we have the values from -1 to 1 for y represented. So I would go from here to here, okay? You notice we could go the opposite way also, right? We could go backwards, but, usually we prefer to work with positive numbers instead of negative numbers, so that's probably the reason why they ignored the left side and they went to the right, okay? So they always want the x equals 0 point, and then here they preferred to go to the right side because that would be positive numbers. So here again, we're going to decide that we'll use these points here. And you know that this point here would be x equals pi, because it would be half of the cosine function, right? And so our restricted domain for cosine would range between 0 and pi. Okay. And the restricted range would range between -1 and 1, just like sine does. Okay? What about tangent? Tangent looks kind of like this, if you remember. It goes from -infinity to infinity from the y point of view. Now, from the x point of view, it goes from negative pi over 2 to pi over 2. Okay? And when you reflect it about the y equals x when you reflect it over the y equals x diagonal line, you end up with something that kind of looks like this. Okay? And obviously, you cannot reflect every single cycle of tangent, because remember, like, tangent repeats over and over, so to the left and the right, you also have similar looking functions to the left and right. But if you reflected all of these, you would have a bunch of blue squiggles on top of each other, and it would also violate the vertical line test. So we're going to limit the tangent function to just this single black squiggle here, and eliminate all the ones to the left and the right of these asymptotes here. And as usual, we prefer to have the x equals 0 point represented, so we're going to have this point here. And for the tangent function, it's kind of a no-brainer to say, okay, I'm going to include this part and this part, which is within these pair of asymptotes. That's going to be my representative tangent cycle, and that's the one I'm going to use to generate my arctangent function. So let's put those values here. So the restricted domain would be from negative pi to pi over 2. It looks a lot similar to the restricted domain for sine, except for you notice how sine has less than or equal to for both the left and the right side, and for tangent we have less than only. The reason why is because remember the tangent is bordered by two asymptotes, so the x value cannot take on the value of negative pi over 2 exactly. It's greater than or less than these values. Okay? And then, of course, the y values that the black squiggle can take on go from negative infinity to infinity. So we write that it's from y is all real numbers. Okay. Now, to find the domain and range for the inverse function, all we need to do is take the restricted range, and put it for the domain, and put the restricted domain in for the range. Because basically, all you're doing is you are turning the function kind of on its side by reflecting it over the y equals x diagonal line, and you generate kind of this blue function here for tangent. And then each one of these also is just reflected similarly to what we saw on the previous page, right? So I am just going to rewrite the same thing for domain and range, except I'm going to put the range value in for domain, the domain value for range, and I'm going to change the x's to y's and y's to x's. So, like, for example, domain for arcsine should be -1 less than or equal to x less than or equal to 1. The range value would be negative pi over 2 less than or equal to y less than or equal to pi over 2. Okay? And then for arc cosine, the x value would be the same as for arcsine. And then the range value would be between 0 and pi, and with less than or equal to. And then finally the tangent values, x is all real numbers, would be the domain, and then the range would be negative pi over 2 to pi over 2. But in this case, we are going to put less than signs only. Okay? All right. Number 2. Find, giving your answer in radians. It says, what is the arc cosine of 1? Okay, so the arc cosine of 1, we could do this in several ways. We could look at the graph, right? So the cosine value is like this. So the arc cosine means take your value of y to be 1, which would be here. What is the x value that corresponds to that? It would be x equals 0, right? So I'm going to put x equals 0, and that would be 0 radians, but 0 radians is the same thing as 0 degrees, right? What about c? What is the arctangent of 1? So now we're going to look at the black function, and we're going to say, okay, what if we take the y value of 1? What would the x value correspond to? Well, the x value that would correspond to that would be pi over 4. And let's see why that's true. Okay, so arctangent of 1 is the same thing as saying the tangent of theta equals 1. So what value of theta gives us a tangent of 1? It would be like 45 degrees, or 45 degrees plus 360 degrees. Actually, for tangent, 45 degrees, you could add 180 degrees to that. It would also give you a value which gives you a tangent of 1, because tangent is positive in the first and the third quadrants, right? So I am going to put I'm going to put the number in radians. So I'm going to put pi over 4. Okay. And that the pi over 4 is in the range, that is specified here because it's between negative pi over 2 and pi over 2. If I would give a value, the next value, which would be 180 plus 45, it would be 225. 225 is outside this range, so that's not the right answer for in this case. What about arcsine of a half? So arcsine of a half is saying what angle has a sine of a half? And if you remember from unit circle, that would be a triangle that has an opposite of 1 and a hypotenuse of 2. That would be a 30, 60, 90 triangle, and it would be the narrower side, which would be 30 degrees. So it would be pi over 6, right? Okay. What about G? Arctangent the square root of 3. So in this case, we're looking for a triangle that has a tangent of square root of 3. And if I drew that triangle, let's see, opposite over adjacent, that means the opposite is square root of 3 and the adjacent is 1. So that would be a 30, 60, 90 triangle, except one that's like taller than it is wide. So basically that would be a 60-degree triangle, which is pi over 3. Okay, and then finally, arctangent of negative 1 over square root of 3. So if I was to draw that triangle, that would be an angle whose tangent is negative 1 over square root of 3. Let's see, that could be, for example, opposite over adjacent. So I would say that that would be, for example, negative 1 over square root of 3. Okay, and actually I drew that kind of weird because actually negative square root of 3 is longer than negative 1, so it should be negative 1 square root of 3 like that. So it looks like it would be like negative 30 degrees, right? Or negative pi over 6. And indeed, the range of arctangent, remember, is between negative pi over 2 and pi over 2, so that's okay to be negative pi over 6. Okay. Finally, inverse cosine of 0.327. Okay, now this you would need a calculator to do. And hold on a second while I put that in my calculator. I got my calculator here. First thing I do is I press mode. I go to the screen. I make sure my calculator is in radians like I want it to be. Then I am going to type in inverse cosine, which you do by second cosine, 0.327. 0.327. Enter. And I get 1.24 for the radians answer. So I'm going to put 1.24 there. Okay? And 1.24, remember, is a little bit less than half a pi. So if you look at our cosine, the range for our cosine is between 0 and pi. So this answer is definitely within the range. So you don't really need to adapt that at all. Okay, let's go to number 3. Find the invariant point for the inverse transformations from sine of x to arc sine of x and cosine of x to arc cosine of x. What they're asking for here is when you do this flip, and let's go back to where we did the flip. We're talking about, I'm gonna draw the flip in purple and maybe a little narrower. And I'm going to show you like which part of the grid we're flipping here. And it looks kind of like this, right? Or it looks kind of like this, right? So they're asking, where does the purple line intersect with the original red function? And the place where it intersects is, of course, along the green diagonal line. And the equation for the green diagonal line, remember, is y equals x. Okay? So let's think about that. So let's take the first part, which is y equals sine of x and y equals arc sine of x. So basically what we're saying is, for these functions, when does y equal x? Y equals x are the points on the green line, and that's what we want to know about these functions. Okay? So basically to do that, we could take one of these functions, y equals sine x, and we're going to say, okay, y equals sine of x, well, we want to know when y equals x, so instead of y equals sine of x, we're going to put x equals sine of x. So basically, we want to know when does sine of x equal x. When you see the answer to this, it's going to be kind of obvious, but just to make it easier to picture, I'm going to put sine of x and y equals x as two functions in the y equals screen. I'm going to graph them, and we're going to take a look at where exactly they intersect, okay? Ooh, interesting. So here we're going to eliminate, or we're going to narrow the window down a little bit. We'll put like negative 4. Negative 4, not negative 40, to positive 4. The reason why I said 4 is because remember that pi is 3.14, and we figure the answer is going to be somewhere between 0 and pi. It's actually going to be even smaller than that, but this will narrow it down quite a bit. Okay, now we're going to graph it. And now we're kind of zoomed in a little bit. And so now it's a little bit easier to see that it looks like it might just intersect right here at the origin, 0, 0. And that really makes sense, right? Because the sine of 0 is 0, right? So they want to know the invariant point for this transformation, and I believe it would be 0, 0. Okay? All right. Now, if we want to like zoom in on this, what we could do is we could change the window size to -1 to 1. And we'll graph it again. And then this time, we could also do a zoom fit so we could see even closer. So we'll do zoom fit. Zoom fit. Okay. Okay, so here's the curve, the sine function, and there is the y equals x function. And it looks like it probably only intersects here at y equals 0, right? So that's where we're going to put our invariant point. What about for cosine of x and arc cosine of x? Let's do the same thing. We're going to put cosine of x and y equals x into the calculator. And then we'll try to figure out where those two are equal. We'll keep the, okay, it's right there, right? So let's try to figure out where that point is. We can figure out where that point is by doing second calc intersect. First curve, yes. Second curve, yes. And then we're going to, it doesn't matter. There's only one apparent intersection, so if we do a guess that's anywhere close to that, it'll give us that intersection. So it says the intersection is 0.739. Okay, so x equals 0.739, or we could say the point is 0.739, and what would be the y value? It would also be 0.739, right? Because we know that the invariant point is along the line y equals x, so the x value has to equal the y value. Okay. Number 4, state the equations of the asymptotes of y equals arctangent of x. Okay, so we know that the for tangent of x, for y equals tangent of x, we know that the asymptotes for y equals tangent of x are going to be x equals pi over 2 and negative pi over 2. And all the multiples of pi added to these, okay? So when we, the two values that we're going to use before we reflect it about the y equals x diagonal line would be these two values here. So when we do reflect these about y equals x, what's going to happen is we are going to get y equals pi over 2 and y equals negative pi over 2. Okay, we're going to get these two asymptotes, right? Because remember, let's go back to this drawing. So remember the blue function here? The blue function here is a version of tangent of x, which is flipped over the y equals x diagonal line, and the asymptotes are also flipped over. And so basically they're horizontal asymptotes, so they'll have the form y equals something, and the something is just going to be the same values as the black asymptotes, which is negative pi over 2 and pi over 2. So those are the two functions. Okay. B, do the functions arcsine of x and arccosine of x have vertical asymptotes? Okay, explain your answer. Well, if you remember what the form of arcsine of x and arccosine of x is, basically arcsine of x looks kind of like this. It looks kind of like that, I think. Let me think. No, I'm sorry. It's the opposite way. Looks kind of like this, right? Because it's the sine function and it's flipped about the y equals x diagonal line. So are there asymptotes to this function? Well, you might say it kind of looks like it has asymptotes. It could have asymptotes that looks kind of like this. But remember, the definition of an asymptote is that it never really touches the asymptote. And in this case, it is touching x equals 1 and x equals negative 1. So no, it doesn't have asymptotes. And arccosine would be the same thing. In arccosine, it looks kind of like, okay, the invariant point would be about here. I think it's kind of like that, right? Okay, and here there's also no vertical asymptotes because it actually touches x equals negative 1 and x equals 1. So no, those are not asymptotes. Okay? All right, last of all, number 5. Simplify these following functions. Okay, so the tricky thing about this is when you look at this, is you might say, oh, arcsine cancels out sine, so the answer is pi over 3. Tangent cancels arctangent, so the answer is 0.3. Arctangent cancels tangent, so the answer is pi. But you have to be careful about that, right? Because, for example, sine of pi over 3, that is going to be, let's draw the triangle, sine of 60 degrees. It would be square root of 3 over 2, okay? Now let's put square root of 3 over 2 in here instead, and then we'll take the arcsine of square root of 3 over 2. Well, luckily in this case, we would come out with the exact same angle of pi over 3, but that's just because we happen to start with an angle that was in the first quadrant. And in the first quadrant, sine and arcsine correspond to each other. Okay, so let's try to do a trickier one. We'll do this one here. We'll do E. So tangent of pi, and then we'll find out what the arctangent of that is. Okay, well, first of all, what is the tangent of pi? Well, pi is 180 degrees, so tangent of pi would be a really flat triangle. So basically, it would be 0 divided by negative 1, which is just 0, right? So we would put 0 in here in the parentheses, and then we'd find the arctangent of 0. Well, it turns out that the arctangent of 0, the most obvious angle that has a tangent of 0 is actually 0, okay? So the answer to this would be angle 0, not angle pi, okay? Because angle pi, yes, it also has a tangent of 0, but it's not the one that's included in the restricted domain and range of the tangent defined by the arctangent function. Okay, so like for example, let's go back and look at the arctangent function. So the only value here in the blue arctangent function that has a value of x equals 0 is y equals 0. So that's why the answer to this is 0 instead of the original input, which is pi. Okay. Now for C here, we can see that the input to arctangent is kind of like a number that is very close to 0, which is already like a good sign, right? So the arctangent of 0.3, let's see, we'll look at that in the opposite way. We'll say, okay, what angle has a tangent of 0.3, so you can see that that would be an angle that's in the first quadrant. And if that's an angle that's in the first quadrant, then when we take the tangent of the angle, we're going to get 0.3 back again, okay? So we know that this one is going to come out to be 0.3. We can reinforce that by doing it in the calculator. We could say, oh, okay, we're going to first look at the inverse tangent of 0.3. We'll get an angle out in radians, 0.291, and then we're going to say, okay, let's take the tangent of this angle, 0.291. What do we get? We get 0.3 back. Okay? All right. And I think that's it for this page.